Hello and welcome to the fifth episode of my operating system development lecture series. Today I'll be talking a little bit about going into long mode, and the main part of that we'll be talking about setting up paging on x86 CPUs. Now, I would like to mention the fact that we're sort of on this fine line between the bootloader and the kernel. And this is because, a bootloader and a kernel are very abstract concepts fundamentally. I mean, they have definitions, but you could apply those definitions to a lot of different programs that do different things. Now, this is generally useful because abstract notions are, in general, very useful because they can be applied to different things. That's the beauty of their abstraction. Now, if it comes to a bootloader, as we know, it is the program that loads the kernel. And since it can't just start executing the kernel code directly, what it does is it sets up a basic environment for the kernel. Now, in general purpose bootloaders, you basically usually the general purpose bootloader boots a kernel in 32-bit, such that all the paging setup and such can be done by the kernel itself, as well as going into long mode. And similarly, also usually a general purpose bootloader expects the kernel to set up its GDT. But I am talking about those things as if they are a part of the bootloader. So, is this correct? Well, sort of. This isn't something that you would want in a general purpose bootloader. However, if you're making some specific bootloader for some specific kernel, this is something that you might want to do. Because if we basically what a bootloader does is we have some kernel in some specified format, and the goal of a bootloader is to load that kernel, start executing kernel code properly. And if we assume that our kernel needs to already have paging set up, as well as the GDT and the entry point should already be running in long mode, then the goal of the bootloader is to provide those things before a kernel is loaded. So this still can be considered the bootloader, although this may not be the common way that things are actually done. Furthermore, I would like to say that this is just setting up paging. Now, obviously, a bootloader shouldn't do such advanced things as actually handling the paging itself. While I will be talking a little bit about that, that is not the main focus of this lecture. The actual kernel mechanisms used for page frame allocation will not be talked so much about in this lecture. However, setting up paging on x86 machines and some general ideas and philosophies related to paging will be talked about in detail. Okay, I think that is everything introductory I wanted to say. So just before I talk about actually getting into long mode by flipping a couple bits, setting up paging, I want to talk about detecting whether long mode is even available. Now, you might think that this is very redundant, because most people are going to be testing their kernels on 64-bit machines. So why would you ever do that? Well, it's just that when I started OSDeving, and I feel like when a lot of people started OSDeving, 32-bit machines were, well, perhaps not the primary way computer science was done, but definitely still a major part of computing. And for one, I remember that my test machine, a test laptop I bought, was a 32-bit machine, and I was developing a 32-bit kernel. And hence, this notion of detecting whether a long mode is even available is very close to my heart, and I sort of wanted to talk about that as well. So the way that one detects the long mode is using this instruction found in most x86 CPUs called CPUID. Now, CPUID is an instruction that helps you identify different information about the CPU that you're using. Now, most assemblers do support just typing the mnemonic like so. If your assembler doesn't, then you will have to execute the opcode manually. Oh well. Um, so the general idea of detecting, okay. So first we have to even detect whether CPU ID exists. Um, So this might seem redundant as well, but this is the proper way that it should be done. In order to detect whether CPU ID exists, what we basically want to do is check if we can flip the 22nd youngest CPU flag. So this is the general idea of what we want to do. Um, so how can we actually check whether we can actually flip this flag? Well, fortunately, x86 CPUs offer this instruction, usually mnemonically written as push F, and it simply pushes the flags onto the stack. Now, usually this isn't the full instruction. I'd say this is just this category of instructions that push those flags, and you usually have to specify the size of the flags that you're going to push. So the instruction that might be used here is push a D, which means push the flags as a D word to the stack. Now, this is going to be very convenient for us in 32-bit protected mode. Obviously, this requires for the stack to be set up. Now, I have probably mentioned this in one of the earlier videos, but in case I haven't, in order to set up a stack, to use a stack, a CPU generally requires two different registers, something called the base pointer and something called the stack pointer. The base pointer is where your stack begins, and the stack pointer is the address of the next element that will be pushed onto the stack, or the ending address of the last element that was pushed onto the stack, however you want to interpret it. So in order to set up a stack, you would have to initialize these two values if they aren't initialized properly. So, for example, somewhere in your bootloader, at the start, you might do something like, in your boot sector, which I guess is a part of your bootloader, you might do move base pointer. Simply put in the address where, for example, boot sector is loaded into the RAM. Move SP BP. So this is an example of stack initialization. but it can do some early on in your boot sector and should generally initialize the stack properly. So once you've pushed the flags onto the stack, you can pop the flags from the stack to some register. This register can be anything. For the sake of simplicity, I'll use arguably the most common 32-bit register, which is the extended A register. Now we will basically create a copy of EAX. So we want to store this value before we actually start messing with the flag values. Now we recall that the store instruction may be used for flipping a bit. So over here we will use it in order to flip the flag. And as I've said, what we want to flip is the 22nd youngest flag. Now, the way we can do this is by storing it with 1 shifted by 21 to the left. This is obviously because if you do a bitwise shift on 1 by 21, you'll get 1 and then 21 zeros. So this specifies the 22nd youngest bit. This is usually called the flag 21 or bit 21 because we consider the youngest bit to have the label of 0. So hence, you can also call this the 21st flag if you consider it to be indexing from 0 or flag number 21. This is also a proper naming for this aforementioned flag. So now that we've modified the value, let us push it onto the stack. Now we will push it because this allows us to pop it back to the flags using the pop fd instruction. So we pop this last D word pushed onto the stack into our flags. Then we're going to push the flags again, and this is going to be in order to check whether we have actually managed to modify it. So let's pop the flags into EAX again. Remember, this might seem pointless to do. These 4 instructions, they might seem pointless because, well, we're pushing EAX, we're popping them to the flags, and we're pushing the flags, and we're popping the flags back to EAX. This seemingly doesn't make any sense. Why would you ever do that? But it actually makes a lot of sense because of the fact that we're going to check whether these flags were modified. Obviously, yes, if we're working under the assumption that this flag can be flipped, then those instructions would be an identity in the sense that they wouldn't do anything to EAX. However, here it allows us to check whether EAX has been actually modified. So now we want to do, I would recommend putting 2 lines as the sort of security measure, because let's go under this assumption that we have indeed managed to flip this flag. So we've performed this test on whether this flag can be flipped. Then it means that this EAX will be different and those flags have been obviously modified. However, we don't really want to modify the flags. This is generally not considered to be a good thing to basically permanently change the flags. We want to do this as a temporary measure in order to check for CPUID support. Hence, we recall the fact that we made a copy ECX, and this was on purpose in order to now push ECX onto the stack and pop it back into the flags. So, if the flags have not been modified, then this is redundant, as obviously this is not going to change anything. However, if they have been modified, this allows us to retrieve the old flags and get them back in their original state. Now, once we've done that, we can finally perform the last check, which is, have we been able to modify the flag? And we can do this using XOR instruction. So we simply perform XOR on EAX and ECX. So we can think of the XOR instruction as an instruction of being different, right? That is because if we recall the XOR gate, then 0, 0 gives us 0, 1, 0 gives us 1, 0, 1 gives us 1, but 1, 1 gives us 0. So XOR is really an instruction that informs us, are the bits different? And this means that if EAX and ECX are perfectly the same, it will always return the 0. This means that at no point should the CPU as 0 flag actually be switched to wait. I sort of lost track of what I'm saying. So we're XORing them, and if they're the same, then we should always get a 0. However, if they happen to be different at any point, then we will see a 1, and hence the 0 flag should be set to 0. So, again, upon performing this instruction, if everything is the same, then the 0 flag will be continuously set to 1, as we will get 0 as a result. However, if at any point they happen to be different, we will happen to have a 1, therefore the 0 flag will not be active. And therefore, we can simply use a conditional jump instruction, JZ, which means a jump if the 0 flag is set. We simply jump some address at which we have instructions related to having some error, or we can jump to a label called error, or error no CPUID, whatever you want to call it. With the key idea being that if the 0 flag is set, then it means that these are the same, so we have not changed anything. Therefore, CPUID doesn't exist because we cannot flip the 22nd youngest flag, or flag number 21. Okay, so this is the whole CPUID detection mechanism. Once we have CPUID, there's one more thing that we have to check for before we can actually get the information about whether long mode is supported. So, not only do we have to check, now we know that CPUID exists if we have not jumped to our error label. However, we do not know if CPUID extended functionality is supported. This is very important because detecting long mode is actually an extend function of CPUID. The reason for that is because, obviously, back in the day, a lot of CPUs did not even consider long mode. and hence, originally when CPUID was made, they didn't even think of a functionality to detect whether a 64-bit processor mode is available. So it was added to the extended functionality of the CPUID. So, this is still available on most 32-bit CPUs, so you don't have to worry, but it's still good to check, and it's actually very simple. The extended functionality, or first I should probably talk about how CPUID even works. What is the idea of CPU? CPUID isn't just an instruction with a given opcode, which doesn't really take any operands, but it does actually use a parameter, which is the what instruction do we want to give to the CPUID? So what sort of information do we want to get and such? And that is stored in the extended A register. And the first, so extended CPU instructions start at the address, well, not address, they start with the instruction ID of 8000. This is obviously in a hexadecimal. 0000. So this is a 32-bit value that goes into EAX, and this is where the extended functionality starts at. And in fact, the very first of those instructions with this very ID is the instruction of, hey, are those extended functions even supported? So the fundamental idea of this instruction, and the implementation varies from CPU to CPU, but the thing that they agree on, this common element of this implementation, is that the EAX register should get bigger, should get larger somehow, by some amount. This is the thing that they agree on. So the EAX register should get larger. So, the idea is that you move this ID into EAX, and you perform the CPUID instruction of your CPU, and then you simply perform a comparison of EAX and a value that is above, just one above. 0, 0, 0, 0, 0, 0, 0. And then, if in the comparison you find out that this value is below, this should be 1, right? If this value is below, then it means that it hasn't changed, and this is not a good sign, because EAX should have gotten bigger. But apparently, if it's not even equal to value 1 bigger, then it's not greater than that, and it's not greater than its original value, and hence the extended CPUID functionality is not supported. So if the below flag is set, then we simply jump to some error label, because CPUID extended functionality is not supported. Now, if we have been absolutely sure that the CPUID extended functionality is supported, then we can actually use the very next function of the CPUID. So we simply use the ID 80000001. We perform a CPUID, and now it's going to store various CPU information in the different CPU registers. The one that interests us is the 30th youngest bit of the EDX register, which can be considered bit 29. So if that bit is 1, then we know that long mode is indeed supported. So we can use the x86 test instruction. So we use the test instruction on EDX, and 1 shifted by 29. And as probably the informed viewer knows, the test instruction, the x86 test instruction, it basically performs an AND gate on all the individual bits. And the idea is that if we take a look at this value, this is just going to be 0, 0, then a 1, and then 29 zeros. And because of that, we know that literally no AND gate will be triggered except for this one potential one on the 30th youngest bit. And if it is triggered, then it means that both are 1, so that bit was 1, so the longbow bit was 1, and hence longbow is supported. So this means that the 0 flag will not be set, because this will not result in a 0, this will result in a 1 from the AND gate. Therefore, implying that a long mode is enabled. Well, not enabled, but supported. So we can just perform a conditional jump instruction JZ to some error, because we know that this is not supported by our CPU if the 0 flag is set. So no result of this. Okay, great. So that was detecting long mode. Now let's talk about paging. I don't even know where to start. I mean, I do because I've practiced this, but let's just say that this is still sort of a dilemma that I've had every time I practice this, and I still do have. Because paging is a very broad topic. But first, I should just say that it is a virtual memory management technique. Now, what does that actually mean? Well, you have some of your physical memory. So you have your RAM, your physical RAM that is actually found in your computer. And many times throughout this series, I've already talked about memory addresses. For example, real mode addressing and such. Now, these were all physical. And what I mean by that is a physical address points you to where physically you can find something on the RAM. Well, in a modern computer, the RAM has like a matrix-like structure, and it's a sort of dynamic RAM because you have a single transistor and a capacitor. It's not static with the latches, but I'm going to electronics now. Point is, using the physical address and a very small amount of information from a manufacturer, you can physically figure out where you could take a voltmeter, put it to your RAM, and get some voltage. It physically tells you where can you find this in your RAM. So that's a physical address, and this concept of physical memory. And it's the most intuitive one. Why would you have any abstraction? However, as we know, abstraction can be very useful. And hence, it's usually good to not only manage this physical memory, but usually you also have something called virtual memory, which comes with its own virtual address space. Now, I could have visualized physical memory just like this sort of even RAM stick. However, it is very difficult to visualize virtual memory. That is because it can have very different forms, it can be non-linear, it may not even be modeled in something that resembles Euclidean geometry. However, I will still allow myself, for the sake of simplicity, to draw it as a rectangle. And we have some virtual address from our virtual address space, which points to the virtual memory, but the key part is that doesn't tell us literally anything about where this data is actually physically found in the RAM. This is fully logical, this is fully virtual. This is for your kernel, this is for your potential applications, programs, processes. This is not something physical. So a physical address tells you where something is actually found in the RAM, whereas a virtual address doesn't. However, virtual memory may be way easier to handle. And for that, I will probably start out with a very simple on a conceptual level, at least if most of the basics, virtual memory management technique that I'll talk about before I talk about paging, and that is segmentation. So the idea of segmentation is that you basically split your memory into segments that are physically found in the RAM. And all of them can be somehow abstractly managed in your virtual memory. And one thing that I should mention is segmentation is supported and even enforced in a way in x86 CPUs. Let's just think about the GDT that I talked about in the previous episode. Well, we clearly had to deal with defining segments. We made segment descriptors, and those are actual physical segments, well, virtual segments, but those are actual segments that the CPU handles. And the idea is that those segments can use virtual address spaces, and these segments, they can overlap, and they're not necessarily like right after each other in memory. They may be in different places. They can be mapped in different ways to virtual addresses, and they can also offer this form of protection, for example, where a given process gets a dedicated let's just have an actual example of when you run some process in the user space, you can have a segment of memory that is dedicated to that process. The process knows how to deal with that in terms of virtual memory. But this isn't a good representation. And then you have this physical segment, which is, well, virtual segment which has bounds in your physical memory, which can be managed in a virtual way, in a virtual address space. It also serves a form of protection where, for example, if a process tries to act on something that is not inside of a segment, you can trigger a segmentation fault, which means that you've accessed something that you shouldn't have accessed. And segmentation and paging are not mutually exclusive. They can both be found in an operating system. So another technique, virtual memory management technique, that can be found on as natively supported by x86 CPUs and a lot of other CPUs, is something called paging. Now, paging does the following. You consider your physical memory to be split into equally sized chunks. And I cannot draw equally sized chunks, so just imagine that they're equally sized, and they're called frames. So this is a physical frame. And what paging does is it splits your virtual memory into equally sized chunks called pages. Now, again, this is a very simple visual representation, but it makes sense for frames to be equally sized and placed, neatly, right after the other. Well, actually, don't have to, but whatever. So it makes sense for frames to be put like that. It makes physical sense. However, when we have virtual memory and we split it into pages, it's a more abstract concept, because you can't even say that a page is after the other, right directly after the other without any space between them, because what does that even mean? We're talking about virtual memory. You could say that a page is after the other in terms of the virtual address space, but that is just an abstraction. It doesn't make any physical sense. But the key idea is that you split your physical memory into equally sized frames, put one after the other, and for your virtual memory, you have pages, and each page is an equal size. Furthermore, the size of a frame must be the same as the size of a page. And this is the general idea of paging. So you have your pages, this virtual concept, and since the frames are the same size, you can put those pages into those frames, and actually only manage the pages, and then have some program in your kernel that puts them wisely into the frames. In fact, you need something called a page frame allocator in your kernel, which is going to dedicate certain frames, which is going to put those pages into them. And basically, paging allows you to do some things that this extra layer of abstraction allows you to do. So, for example, let's say we have some data. We have some 4 kilobytes of data. 4 kilobytes is a pretty standard size for a page. Let's say we have some data, and we have some 2 processes, P1 and P2, that want to access that data. So let's say that those 4 kilobytes were just to be somewhere physically on in the RAM. Well, in that case, you might encounter something like a critical section problem, or you might have some reading failures and such. However, if you consider those 4 kilobytes to be in this virtual concept called a page, to which both processes can access through the same virtual address, but for example, the page may be given to 2 different physical frames such that it can be securely accessed. This allows for this security through an extra layer of abstraction. And generally, managing those pages and data in those pages can be way more convenient than managing this data in the physical memory itself. So paging really allows you to do different things. Another example of what paging can allow you to do is basically, and this is actually a very common element of paging on most operating systems that use it, is and it's often considered part of paging itself, is you have some part of your disk. You have some part of your disk and a part of it is also dedicated for storing pages. So not only are pages found somewhere in your RAM, they're stored in your RAM, and they also may be stored on a part of your disk. And then you can use this technique called swapping, and you can basically put the pages in the frames, or pages can be found somewhere in the frames as a virtual concept. You can basically do some very cool things as this abstraction. Okay. So this may seem pretty daunting. How are we actually going to set all of this up? And basically, we don't really have to care about most of these abstractions just to set paging up in a minimal standard, because we can do something called identity mapping. So, as you might know, for example, in linear algebra, an identity matrix is a matrix that does nothing to the vector that it's multiplied by. And for example, in multiplication, one is often called the identity element because multiplied by anything, but by any real number, actually complex as well, but whatever, it gives the same number. So if you're familiar with the notion of an identity map in mathematics, this is basically the same thing. An identity mapping basically means that all the virtual addresses will be mapped to one-to-one to physical addresses. So I said that a virtual address doesn't actually tell you where something physically is in your physical memory. And this is sort of true, but the thing is, if you set it up in a way that it's the same, if you set up, well, okay, so it doesn't tell you where something is in the physical memory, but it can obviously access that information in some way. So you usually have like a address translator, right? So you have some virtual address that points to some element of your virtual memory, and in your kernel or whatever, you're going to have an address translator, which will tell you where that can actually be found in the physical memory. So over in our example with the identity map, we can make the simplest translator ever just do nothing, because our virtual addresses are going to be the same as our physical addresses. So this is an identity map. So, is this a good solution? Well, it's definitely simple and it might be a good starting point, but generally no, because it has many disadvantages in the long term. For example, your processes may want to access the frame buffer. So the frame buffer, if you don't know, when you have a video card or a graphics card, in order to actually send information, it takes some information about what it should draw, so that then it can take it and process it into signals that it gives to your display. So that information about what it should draw is usually given in something called a frame buffer. And a frame buffer fundamentally is just some part of a RAM. So in the RAM, you have a dedicated section of the RAM, which is your frame buffer. And it is not necessarily. And so the thing is, your frame buffer, depending on your video card, depending on the video mode, depending on your graphics card, everything, it may be found in different physical addresses. So, for example, most virtual machines or emulators put the frame buffer as the address FB000000, where FB stands for frame buffer. Some real hardware does that, but generally it's just found in the documentation, or it's actually best to get that information that I'll probably talk about when I'll be talking about setting a video mode and such. But that's not such a priority. Having nice graphics in your OS is nice, but it probably shouldn't be your priority. But whatever, it's you. I'm not here to dictate what you should do or not. You're a free human being. But yeah. So what I said is you have those different addresses of where your frame buffer starts and, well, ends, and they might be in different places in your physical memory. However, this isn't good, or at least it's not that good to always make everything access it through that address, which may change. Usually, very good solution is for the physical address to be different, but the virtual address, so in your virtual address space that your processes will actually use, you want the virtual address of the frame buffer to be always the same. And this is just one example, and generally there are many ways in which an identity map is not the best solution, and page cloning and other techniques may not necessarily be accessible. That out of the way, let's talk a bit about the different paging levels. So, the simplest conceptually is one-level paging. The idea of one-level paging is you simply have a page table. So a page table is supposed to be a structure that contains different addresses of the pages, and the different virtual addresses of the pages, the different information about the pages, the flags and everything. All of the page information is just stored in one big table. Okay, cool. Very simple conceptually. When there's two-level paging, and the idea of two-level paging was to introduce this extra layer of abstraction, which is a page directory. So you would have a page directory table, and page directories, basically, you can sort of intuitively guess what they are. They're both sort of collections of, for example, related pages, such that you can group pages that they can be related to each other. This can be used for wiser managing of your virtual memory. So you have this, and it points to different page tables. It is also worth mentioning that all those all of those tables are usually, at least on x86 CPUs, they are all 4 kilobytes, which, by the way, is the standard page size. But I will come back to standard page sizes later. Okay, so pre-level paging. It basically introduced an even higher level of abstraction that was meant to extend this, and you had a page directory pointer table. So you have a table of pointers to those page directory tables. So they would point to PDTs, and those PDTs would then point to PTs, or page tables. So this is pre-level paging. And then, obviously, they wanted to continue to extend this to allow for more RAM access and such. And this is actually the current, I'd say, standard. And that's 4-level paging. So I believe this is the easiest one to currently set up on x86 machines. It is, I'd say, the general standard both for, hobby operating system developers as well as just for normal users. You're probably using 4-level paging right now if you're using an x86 machine, unless you've configured it to do so. That is because 5-level paging, it allows for addressing really a lot of RAM. And 4-level paging already allows for addressing, I think, 256 terabytes of virtual memory. So really, only like very specific solutions really require 5-level paging, and the average user usually doesn't. So far, 4-level paging is really standard in most x86 machines as of right now. And 4-level paging simply introduces something called the page map level 4 table, PML4T. And that points to page directory pointer tables, which points to page directory tables, which actually points to page tables. Now, this might seem daunting because, well, if we have to do all of that, then it might seem that we need to set up a very advanced structure. However, that is not necessarily the case, because we can actually do this in a way easier setup, which is 4-level linear paging. Now, it fundamentally doesn't really differ that much from 1-level paging. It's sort of the same, except realistically on modern machines, it's way easier to actually turn on the standard 4-level paging, and also on Intel CPUs and such offers some extra functionality. It's way easier to do that than 1-level paging, and you already have a structure set up that allows you to always change this, modify it, and make it more advanced and use all of those concepts. However, just to set paging up, we can make a linear structure, which is basically just that we have a page map level 4 table. It points to one page directory pointer table, which points to one page directory table, which in turn points to one page table. So fundamentally, we only have one page table. However, at any moment, we could, for example, add an extra page table or even an extra page directory table, and so on and so on. We could really play around with the structure. It's going to offer some extra functionality, such as PAE paging, which I'm going to talk about, and it's just going to be easier. So it's each of those tables, as they've said, they take up 4 kilobytes, and we can start by setting up the page map level 4 table, but pretty much will be empty except the first entry. So at the very address that we say that PML4T begins, and we'll set this in control register 3 later, where we'll show where our PML4T is. The first entry will simply be a pointer to our PDPT, together with some flags. So we have our PML4T, which, let's say we can, for example, put it at hexadecimal 1000. That is because usually the first 4 kilobytes are considered reserved. You probably want to do something like this. Okay, great. So now we know that at this address we'll have our PML4T. We'll let the CPU know that later with the control register 3. And the idea is that the first entry will point to the PDPT. So knowing that we can place the PDPT just right after our PML4T, and the PML4T is 4 kilobytes. 4 kilobytes, so that's 4096 bytes. 4096 in hex is 1000. So we can simply move into the address of a PML4T. So there is 1000. We can simply put 0x2000, except we might actually want to set some flags. So paging flags, regular flags, but maybe used by pages, and they're also used by the tables related to paging. So let's just talk about, there are a lot of those bits, right, which correspond to those flags. For now, I'll only talk about 3 flags that are really going to matter. The first is the present flag, which we obviously want to be 1. The next one is the read-write flag, which we also want to be 1. However, the next one, okay, let's just say, so 1 1, right? So in binary, that's going to be 3. That's actually all the flags that we're going to need. So we simply place the value of 3 at the end. So now we're pointing to the PDPT with those flags. Now, the next one, for us is going to be 0. However, this is actually a flag that will definitely be very important later to consider. And that is because this flag right over here is the supervisor / user. So if you don't know, supervisor is the term for anything that has these very high permissions. So that's going to be the bootloader, that's going to be the kernel, potentially drivers and so. That's called supervisor mode. And supervisor is going to have 0. Since we're currently just setting up some paging, we're making a paging setup that our kernel will use. It doesn't affect us. We want it to be 0 because 0 core always is going to correspond to supervisor. However, later in the user space, it will throw general protection faults on trying to access pages that have this supervisor flag, supervisor user flag set to 0, because it means that it should only be accessed in supervisor mode. So for pages that will have to use in the user space, this has to be a 1. Hence, this in binary is, in decimal, converting from binary is 7. So this 3 will actually turn into a 7 if it comes to user pages. However, for now, we don't really have to care about that because we'll be executing everything in supervisor mode. Also, a little remark, sometimes, this is quite rare, but you might see it somewhere in some technical documentation and such. The supervisor mode may also be called the monitor mode. And that's actually how we call it over here in Poland. We call it tryb monitora. That's how I get to hear it in the lectures that I attend IRL. So, right, we move this address of our PDPT with the flags, and we pretty much have our whole PML4T set up. So now, as we've said, our PDPT is at this address, and now we want the first entry of our PDPT to point to our PDT, or page directory table. So again, since the PDPT is 4 kilobytes, and if we convert all that to hexadecimal, right, that's just flipping us one further, so it's going to, we know that our PDT is going to be at the address 3000. So we move into 0x2000, we move 3003, right? Because we have to remember about the flag. Then, right, the PDT is at this address, as I've said, and our first entry of the PDT is going to point to our page table. Okay, so again, let's say that our page table is at 4000, hence we move into 300. We move 400 with 3 as the flags. Okay, a quick remark, let's just add over here PT as at 0x44000. So this is our setup of all the tables. Obviously, only those are actual assembly instructions. This is literally everything that you need in order to do this linear 4-level linear paging setup. Okay, so now that we have all of this, so we have our general paging structure, the last thing that is remaining is to actually fill our page table. So, the page table, like any other table that was previously mentioned, is 4 kilobytes. So this means that we have 4,096 bytes, and we are going to fill it with different virtual addresses of our pages. The virtual addresses that we desire. Right. So it is then going to map those in correspondence to the different physical addresses that we have. So we want to make an identity map. So we don't really have to care. We're just going to place them neatly such that those pages directly correspond to our physical frames. So pretty much the structure of the page table is it is split into those 4-byte chunks. And these are going to store our address together with the flags. I think something might not be checking out my notes that I've prepared. So I will allow myself for a quick pause in order to verify this information because I've written those notes a couple months ago, so they might not be fully accurate. Okay, yeah, so I'm pretty sure that one keyword that I've written down is wrong because I said that both uh, the page table and both 4-byte chunks it stores the virtual memory address, which is actually not correct. I've looked at this. I always try to verify what I'm thinking with my notes in order to not make a mistake, but apparently now it was the other way around. My intuition said the correct thing, while apparently the notes I've written down were not correct. The page table does not store virtual addresses. The next virtual addresses that you have are so basically this 4-byte corresponds to your virtual address space where you pick a page size, let's say 4 kilobytes, and all of them are going to correspond to next 4 kilobytes of your virtual address space. And you can't change that. What you do change in this page table is that over here in the 4 bytes of the page table, you actually place the physical, not virtual address. So over here, you place the physical address, and therefore, that's how you do this mapping. So, I really wanted to make sure because since we're doing an identity map and our virtual addresses and physical addresses are going to be the same, it doesn't matter here. And if anyone is following along, they would get it working and they would not have a good conceptual understanding. And a good conceptual understanding is really what I'm trying to reach with this series. So I highly apologize for um, this mistake that almost occurred here. But this is a physical address that is stored in the page table that will be mapped to those statically dedicated virtual address space elements. So you have this page table, and you have those 4 bytes, and you have to fill them with the next physical addresses that you want, corresponding to your virtual address space. So the virtual, so the page sizes that x86 offers are the following. You can have a 4 kilobyte page, which is really it's really standard. You can have a 2 megabyte page, or you have 1 gigabyte pages, which are often critiqued for being way too large, but they do have some practical usage. Yeah, so pick a page size. Uh, most setups do use 4 kilobyte pages. So let's actually fill in our page table. I'll write down a little assembly procedure in Intel syntax. We will use the ECX register for counting. So we want to execute this procedure 512 times, and that is because, as I've said, the whole page table is 4,096 bytes, as it is 4 kilobytes. Now, I said that one entry is 4 bytes. Now, obviously, the bytes cancel out, and 4,096 divided by 4, that would be 1,024. That doesn't check out. Oh my god, I highly apologize for the amount of mistakes. So, those entries are actually 8 bytes. This is okay, so we want to store 32-bit physical addresses. Oh my goodness. I really apologize. I'm extremely sorry. I have done a way too large amount of just conceptually wrong things. So 32-bit physical addresses. 32-bit. So obviously when you store a 32-bit physical address, 32 bits is what's 4 bytes. That is Okay. Let's just focus on the identity map. One entry is definitely 8 bytes. And that is because of, okay. So we're actually setting up something, and I was going to talk about that a bit later, about what we're actually trying to do, but we're trying to do something called PAE paging. And in PAE, it stands for Physical Address Extension. So the idea is that usually you have a 32-bit physical address, and that allows you for addressing 4 gigabytes of memory. Now, this isn't necessarily sufficient for many users, hence I wanted to set up PAE paging, which allows you to go over that 4 gigabyte mark. And in that setup and PAE paging, the entries are 8 bytes. Oh my goodness. I highly apologize again. So again, 4096 bytes. We divided by 8 bytes for an entry, and that is 512. So we have to execute the procedure 512 times. Okay. So we can define a label, something like ID map or identity map, and we perform the following. So I will do it is I will first move the page size into the EAX register. This isn't for any hardware reason, this is just how this identity map algorithm will work. So, as one may notice, I have chosen a 4 kilobyte page size. So that's 4096 bytes. 4096 is the following number in hexadecimal. If I would have chosen a 2 megabyte page size, then I would have to convert 2 times 1024, that would be in kilobytes, and 2024, that would be the value in bytes, and you would have to convert that to hexadecimal in order to get number. I mean, you don't have to put it over here in hexadecimal, obviously. You can literally just put, you can just put 4096. Or if it was 2 megabytes, just whatever 2 times 1024. This is 1024. This actually shouldn't be difficult because this is 2 to the 10th times 2 to the 10th times 2, so that's 2 to the 21st. So if you just calculate 2 to the 21st and you put that in over here, nobody's obviously forcing you to use a given number system. It's just generally common to write a page size in whatever context in hexadecimal. However, that is obviously not a requirement. I can just put 4096 here. I'll just use this in order to portray addressing in an easier way, because memory addresses are usually written in hexadecimal. So the idea is to multiply this by the counter. And this makes sense because we'll get to the next physical addresses. So over here, we'll start with 0. And this means that when we set this to 1000 and we multiply by 0, we'll get 0. That is great. The address of our first page is 0. Everything checks out. Now we want to add our flags, so I'll just OR it, or our EAX, or the result of the multiplication is always stored with 10000011 for our flags over here. Now we can actually move it into our page table. So that is going to be address plus ECX times 8. Right? Because an entry is 8 bytes. So every time we want to give an address to a new entry, we have to move it by 8 bytes. And we simply move the value of EAX there. So we move into our page table into ECX times 8, that's just going to be 0. So index 0, first entry over here is going to be the address 0. So then we're going to increment ECX and pair ECX with 512. And if they're not equal, then we want to go back to the beginning of our label. So this is a very simple algorithm for creating an identity map. So we start with this counter, and basically we pick our page size that we're going to be increasing our addresses by. So we multiply it by ECX, so first it's going to be 0, we add our flags, and we put it into our page table. We increment the ECX, it's not equal to 512, so we jump back, but now it's incremented. Now that we multiply it, the next page, we add the physical address of the next frame in which our page will be in, is going to be 1000, because 1000 multiplied by 1 is just going to be itself. We have a flag, we put it as the next entry because now we're going to add 1 times 8, right? So we move 1 entry because 1 entry is 8 bytes, right? Every address corresponds to 1 byte. We increment ECX again, it's not equal to 512. Again, we start from the beginning of our algorithm. So we have EAX multiplied by ECX, so now it's going to be this times 2. So the next is going to be 0x2000. It's going to be the next address, the next physical address. And that our page size is 4 kilobytes, then we're making this correspondence between those virtual addresses to the same physical addresses because they're so neatly packed on the code. And we do this, eventually we're going to hit 512, and we're going to stop the identity map. And everything is going to be put into the page table, and hence all the physical addresses are going to be mapped to all the virtual addresses. That's the whole review. Okay. So now we want to specify that we want PAE paging, which I previously mentioned. And actually, before that, let me just point out that instead, we need to somehow inform the CPU where our PML4T table is, and we can do this using the control register 3. So, we can't move a value into CR, directly. However, we may move, for example, into EAX 0x 1000, I believe was the address of our PML4T, and then you just move into CR3 the contents of EAX. So something like this should probably work. Okay, so now that we have this, by the CR3 register we've established where the PML4T is, we can actually enable will not enable PAE paging, but enable the bit that tells the CPU that when paging will be enabled, it shall be PAE. And this is the 6th youngest bit of control register number 4. So we can't perform operations of the control registers directly, so we have to move into some register like EAX. We have to move the contents of CR4. Then we may actually set the bits. I'll use the OR instruction just in case the bits is actually set, like with the A20 line. So OR EAX, and again, 6 youngest bits, so we can shift 1 left by 5 places actually. 5, right, if we want the 6th youngest bit, because it's going to be bit number 5, with the youngest, complete youngest being 0. And then we move it back into the control register 4. Therefore, now the CPU knows that we want physical address extension paging. Now we also want to say that this paging will be used in long mode in order to actually get into long mode. So after enabling paging, we also want long mode, right? And this is actually done through a model-specific register. Now, this might seem quite peculiar. Why would you do it for a model-specific register if we're talking about general x86 CPUs? And the reason for that is because, obviously, when back in the day when registers were designed for 16-bit and 32-bit CPUs, people didn't really care about a 64-bit CPU mode, or at least they weren't considering one realistically. In practical terms of designing different things. So the register that actually contains this information about this long mode bit that we want to actually flip, or at least enable, is not in any of the control registers, but it's in a model-specific register. And that's because first, initially, there were some specific models of CPUs that had long mode, and it was a model-specific register for those CPUs that allowed you to turn on long mode. However, now it is the standard, but it is still a model-specific register, and you have to access it as such. Now, in case someone is not familiar with model-specific registers and the mechanisms of interacting with them, you basically have 2 instructions. Read model-specific register and write model-specific register. And they both work in a very similar way. Basically, the ECX register contains the ID of the model-specific register that we want to access, while EAX contains the content. So in the write, the EAX register is going to be written to the model-specific register with the ID provided in ECX. When we're reading, it will take the model-specific register with the ID specified in ECX and will read it into EAX. So the model-specific register that we are looking for has the ID C000080, if I'm not mistaken. That should be right. So we read it. Now we know that this model-specific register has been read into EAX. So now we simply have to take action on the 9th youngest bit. And by 9th, I mean that we shifted by 8. So this is bit number 8. So the 9th youngest bit is responsible for, hey, do we want to enable long mode when we enable paging. So we simply OR it. We could store it, but just in case if this bit is already set to 1 and we don't want to disable this feature, so we OR it. In a sim, we've done this thing many times before, right? And we write it back to our model specific register as the ECX register should not have changed, and our EAX register has been modified to what we want it to be. Right, so now we've told the CPU that we want PAE paging and that we want longbound paging. So now let's actually enable it. So in the CR3 register, we specified where the PML4T is, and we've made the PML4T points to the PDPT, we made the PDPT points to the PDT points to the page table, and we've identity mapped the page table with a little bit of trouble, which I, again, apologize for. I really don't know how it didn't come out in my practice sessions. So now let's enable paging itself, and that's very easy. We simply have to flip the oldest bit this time in the control register 0. Since we cannot access it directly, again, let's have a value to EAX, and let's OR it just in case the bit is flipped. This shouldn't be the case. The bit shouldn't be 1, but just in case, again, it's better than just XORing it. So let's OR EAX, and we still usually just write 1 shifted to 31 to signify the oldest bit, because it is sort of bit 31. Usually, so this is just the general way when the technical documentation tells you it's bit number n, then usually you'll have it represented as 1 shifted by n to the left. Even though you can call it the 32nd youngest bit or the oldest bit, no matter what you name it, you usually want to follow this convention. This is once you've actually done this, you obviously have to move it back to control register 0, and congrats. That is pretty much it. We're currently in something called compatibility mode, and that is because we're not executing 64-bit code quite yet, but we're basically in line. The thing that really remains if we want to execute 64-bit instructions is simply perform the so-called far jump as with 32-bit protected mode. So, okay. One more thing, actually, that we should do in compatibility mode, that I remember now, and I probably have my notes as well. We should edit the GDT. So, as one might remember, in the GDT, there was a certain flags entry. So there was a byte that was the flags have 4 bits of the limit address. Now it has to be modified because there was a size flag and a long mode flag. There was a granularity and reserved, right? And if it comes to the size and the long bits, right? But the long bit was set to 0 because I was talking about going into 32-bit protected mode, not going into long mode. As for the size, it was set to 1, which means that we want 32-bit protected mode. This shall be changed. So this is a very, very small change, we had 1 here, we had 0 here for reserved, obviously, and then we had 4 bits of the limit, which was 1, 1, 1, 1. Now we want the long mode bit to be 1, as we're going to long mode. To be 1. As for the signs bit, well, if the long mode bit is 1, then the signs bit should always be 0, and this means a long mode setup. So this is one slight modification that we have to do to the GDT in order to execute 64-bit code properly. Okay. So this is very easy. While still in compatibility mode, we simply move into the code descriptor byte and the data descriptor byte, this byte that contains this info, we have to simply move 10101111 in binary. Yeah, so that's that should be simple if you either exactly know the address of where it is, or if you have defined a label. If you define a label, such as code descriptor, code desk, something like that, then you simply add 5 to it, so 5 bytes further. And yeah, if you move by 5 bytes, it should be at not equals. Move into this a byte 10101111B. Very simple, and then just do the same for the data descriptor. So data descriptor plus 5, and then the same bytes. So this is the slight GDT modification that one has to do. It's very quick if you have labels for that. If you don't, it's still pretty simple. You just calculate the address of your code descriptor and your data descriptor, and you add 5 to it. Should be 5. If 5 doesn't work, do 6, but I'm pretty sure it's 5. Okay, and this really should be everything that we have to do in compatibility mode. Now we can just jump to the actual 64-bit code. So in your code, you would have a section that would be like bits 64 or something like that. You would define a label like, I don't know, LM for long mode or whatever. You can have an infinite jump instruction here. We don't really have to do all the flushing like we did with protected mode. So really, simply, in compatibility mode here, just do a jump. As a segment, you should have your code segment, which will be your 8 per 16. So we just do a far jump to LM. Yeah, and that's literally it. If the detection of the long mode support was successful, and if paging has been set up successfully, the GDT has been modified, and this far jump is performed, then code should be executing in 64-bit long mode. Just to test that, one might, for example, play around with the registers that begin with R, right? Which stands for register, by the way. So those are 64-bit CPU registers. One might, for example, use what instructions, right? Instructions that you would use D4 at the end for D word, and now you could use Q for Q word, quadruple word. You can really mess with those things. But that's basically how to get into long mode. So that's everything I wanted to talk about. I highly apologize for all the mistakes that were related to paging. I also feel like I haven't explained segmentation the best I could. But I hope that I have corrected myself enough in this video. I hope it wasn't too painful to watch. It was fundamentally just like 2 or 3 mistakes, but still. I highly apologize for them. Yeah, and that's pretty much everything I want to talk about. And in the next video, I will be talking about finally getting out of this hell even, and actually developing a kernel, which is where most people start at, and where most people probably should start at, because writing your own bootloader is probably not the best thing to do. And I explained it mainly because there's still people who want to do it, 1, and 2, I feel like it's still quote-unquote cool to be generally educated about some of the internal workings of how these mechanisms work in the x86. And yeah, now I'll be talking about just loading the kernel. It should be definitely a shorter video, and then I'll actually be talking about kernel development, which I think is really the key part of operating system development, is really what it fundamentally boils down to. Okay, thank you very much for watching this lecture. Again, I hope that the couple mistakes I've done were not such a problem. And I hope that you'll watch the next video in this lecture series.